A very good afternoon to everyone. I am Gupta from IIT BHU Varanasi, and this today's topic is intelligent IoT sensing system. So this is not a talk; this is a discussion sort of thing. So if you have any query, questions, suggestions, definitely, and please ask, please raise your hand, and we can discuss at the same time or at the end of the presentation. Both possibilities is there. So let's begin start. So I just switch off the camera so that we can find out good bandwidth and speed properly speeding on the internet. So here we have the two main sessions, section 2 and session 3, that what I have done between 10 to 14, 14 to 16, right now what we are doing. So in this entire presentation, we cover up the 10 years what we have done in this domain, and what is the negative impact, what is the loss, what we are getting, what wrong direction we have selected, what right direction, and what is your feature. So we just cover up that point, that what is the negative. Sometime we have done some mistakes that go in the wrong direction and find out no, there is no outcome in this direction, reverse back and go in the other direction. So that's all these things we will cover up and discuss in this talk. So I'm assuming that you will enjoy in this talk, and if you have any query, question, suggestion, definitely please ask. That always welcome. So here I've done my MTech and PhD from IIT Guwahati, and main work is the sensor deployment during my PhD. Okay, so the sensor deployment, then how we can deploy the sensor so that the region is covered, region is monitored with the help of the sensing region. After that, after deployment, definitely sensor detects some events. Okay, say for example, smoke sensor or fire sensor, they detect some temperature values, some values are there. Now the second challenge is that how we can communicate this information from sensor to a processing device. So there are two ways, either short range communication and or long range communication. So the first, the short range communication comes into the picture. Why? Because these sensors are battery powered. Okay, they have very limited, very small batteries there. We are not assuming that they can use a Wi-Fi or some energy hungry device. No. So they use the short range communication like BLE or Bluetooth. So after deployment, we focus on the BLE mesh network, BLE short range communication in 2015-16 with Samsung R&D Bangalore, and we work on the BLE mesh network. This is right now it's comes into the solutions, whatever the proprietary solution of the Samsung and Bangalore, they use this one mesh network. It's working perfectly. We will see that what is the novelty in this work. After that, if BLE can transmit up to a certain range, then comes to the long range communication. How we can transmit this information remote, that comes into the picture. So here we talk about the long range communication. Then we comes how we can process this information, where we can process the information, and what percentage of the information we can process. So this is the fog computing. And finally, intelligence comes into the picture for artificial intelligence, machine learning, deep learning, game theory, computation geometry approaches that we are using for solving the problem. But before that, we need to transmit this information from the source to the machine where we can process the information. So this is the journey, the 10 years that we find out the path, okay, how we can deploy the sensor, BLE, then long range, then fog, then after intelligence. This work is supported by two funding projects. One is the government funding, other one is the private funding. So this energy efficient wireless sensor network for precision agriculture, where because since this IIT BHU we have the agriculture field is there, BHU has the agriculture farming field is there. So that we deploy the sensor, and periodically we collect the sensor values and transmit these values to the computer lab, whatever our department lab is there, that we can transmit successfully. And same thing, the water to cloud, we collect the sensory data from the water, Ganga water, transmit these values to the lab and doing the processing and other things. So there are two funding projects are there. And recently we finished 3 PhD in this domain. So these 3 are my students. I'm the supervisor of these students. So first is the Dr. Surbhi Saraswat. Right now she's doing the postdoc in UCC Ireland, and their main work is on the fog computing. Okay, then we comes to the LoRa long range with the Preeti, and finally the Ashish, they work on the intelligence early classification. We will see one by one this work. So as the title is that intelligent IoT sensing system, that's very big title and covers a huge field. So if we go right to left, that first comes the sensing. So in this talk or in this entire work, my main focus is on the sensors, not the image. Okay, they are completely different techniques are there. We are not able to say that one technique which is suitable for the image that is also suitable for the sensor. Why? Because there are two challenges. One challenge is that one sensor data is very small, so we are not able to use the heavy machine learnings. Okay, where a huge data is required. And the second challenge is that in the image, if some image information loss is there, then we can also tolerate. Say for example, compress or compression technique where we can lose some image, but sensory it's not acceptable. So door open and close. The binary information 0 and 1. If in place of 0, 1 transmit in place of 1, if we transmit the 0, then nothing to be meaningful that information. So sensory information, we assume that high accuracy. Of course, data size is very less, a very small data is there. So we are not say that, okay, if I have one technique or someone use the image processing technique that we can use directly in the sensor field, or a technique which is suitable for the sensor, which is also suitable for the image. So that's why we especially highlight the IoT sensing system, not IoT systems. And of course, the red color indicate the intelligence. That is the part of the machine learning, deep learning, graph theory, computation geometry, or right now we solve with the help of the game theory. So this red color indicate the intelligence and blue color indicate the IoT sensing system. So if we first cover up that here we have the sensor deployment, then after short range communication, then long range communication, then processing of the data. So sensor deployment, we cover the three major problems. One problem, that border coverage. If we have a field of interest, the field of interest shape is the random. So for simplicity, we consider the convex shape, where the angles of these corners are less than 180 degree. So these are the convex shape field of interest, and we deploy the sensors. We assume that the random deployment, which is suitable where the man-made effects are not possible. Say for example, forest monitoring or some fire monitoring, where we can deploy the randomly sensors. So here the challenge is that the border effect, if the sensor nearby the boundary region, definitely that is not completely useful. Some area is outside the field of interest, which is not useful for coverage or monitoring purpose. So here our main work is to find out what portion of the sensor is useful for the coverage. And based on that one, we can easily identify the density of the sensor, or how many number of sensors we are required for the desired monitoring or desired coverage of the field of interest. So here we use the computation geometry, especially we use the tool of the Bernoulli diagram and the power diagram for finding this one regions. And this work is published in this the given reference. This one. This is the extension of that one previous one work for the 3D. So if there is a swimming pool is there, where that we want to monitor the water quality in the swimming pool or some chlorine level and other things. So the swimming pool shape is the 3 dimension. So definitely the sensor is the 3D sensor, that is the spherical, and their sensing region is less than the spherical sensing region, which is, if we consider the binary sensor, then 4/3 pi r cube. If we consider the probabilistic sensing, then of course there are some probability distribution is there. So this is the extension of the previous one work. The second problem that is also an interesting that, so in some case scenario that we monitor that we are not able to deploy the sensor inside the field of interest. So say for example, this black color indicate the road, or some traffic road is there where vehicles can moving here and there. And this brown color is the footpath of the road, that means nearby the area of the road. So we are not able to deploy the sensor on the road. We can deploy the sensor nearby the road. But when we deploy the sensor nearby the road, then their sensing region is not completely useful. There only this denser sensing region is useful for the monitoring or for the coverage. So the second problem, we consider that, okay, we want to cover this road. How many number of sensors we need to deploy so that the region is covered? So in this case, we also need to find out the effective sensing region, definitely, which is less than the complete sensing region. And we find out the or estimate the sensor density. First and second problem, both we assume that the random deployment and the sensors are deployed randomly in the field of interest. So as the very beginning, we see that, okay, the sensor deployment are there two types. One is the random deployment, other one is the deterministic deployment. In the deterministic deployment, a person man-made effect is there. Either we use the regular pattern, square, hexagon, or triangle, or we can use some pattern in the deterministic deployment. The random deployment, we can randomly deploy with the help of some probability or statistics, for example, Gaussian distribution like this one. Now, both approaches, they have the advantage and disadvantages. In the random deployment, the advantage is that very less effect while deploy the sensors. We just scatter the sensors, so we are not worried about the position. But in the deterministic deployment, the position is the important. And the advantage is that in the deterministic deployment, we need a very less sensor as compared to random deployment. So random deployment wireless sensor network cost is very high as compared to deterministic deployment. And one mathematical analysis says that in the random deployment, you need a 6 times more sensor as compared to the deterministic deployment. That means if we focus on the deterministic deployment, we can reduce the cost up to the 6 times less cost in that case. But random deployment is possible when a person is not able to go, say for example, forest area and other thing. Some research work, they say that okay, if you deploy the randomly, if you focus on the random deployment, even some holes are possible. Because we deploy the randomly, we are not able to 100% sure that the region is covered. So what option is there? We can deploy more sensor what the mathematics says that. So if mathematics says that the 100 sensor, we can deploy the 120, 130 sensors. That way we can do. So the probability of the coverage hole is 0.001% in this case. 100% probability is not possible because that is the infinite if we go to the 100% probability. So in that case, we deploy sensor more than what we are required. Since these sensors are the battery powered, these sensors have no such continuous power supply and other things, and we are also not able to replace these sensors, these batteries. So what options is there? We can use some sleep scheduling protocols. So initially we deploy a large more than what we are required, and then we can use some scheduling protocol so that if a sensor is redundant, that means the region is covered by the other sensor, then the sensor goes down into the sleeping state and other sensors comes into the active state for covering that region. After some time, this sensor goes down in sleeping state and that previous sensor which is in sleepy state, they comes into the active state and covers this region. So this is the sleep scheduling protocol. So initially all sensors in active, then the sensor check that whether I am redundant or not. Yes, I am redundant. My area is covered by other sensors. Then the sensor goes into the sleeping state. After some time, the sensor once again come in active state, working their duties, whatever they are doing, and once again they check that whether I am covered or not. So this sleep scheduling protocol we published in 2016 in Vikla technology paper. And they assume that the 3 dimension, not only the 2 dimension, also consider the heterogeneous, where the sensors have unequal sensing and communication range, not a homogeneous. And of course, we consider the random deployment. So these 3 problems that we addressed in 2013-14 for random deployment of the sensors, where we deploy the randomly in the field of interest. In this slide, I am not covered that, but we also consider the deterministic deployment for indoor navigation system, indoor positioning system, where the sensors are deterministically deployed one after another with the help of mathematics. Now we assume that we are familiar with the deployment and we deploy the sensors for monitoring, for coverage, a given field of interest. The second task is that when a sensor is deployed, they have the property of the sensing. Now how they can transmit their information to the base station. Very first comes in the mind that short range communication. Why? Because they consume the less energy and these sensors are battery powered. So what we are doing in the Samsung R&D Bangalore 2015-16, our main work is on short range communication. We propose a BLE mesh network. This work is published in this conference, IEEE Sensors 2015 conference. And the novelty and the beauty of this solution is that the devices are mobile, devices are not static. So the Samsung designed a mesh network for smartphone, for tablets, for laptop, where the devices are moving here and there. We are not able to assume that yes, these sensors are static and that is static. Another example of mobile devices is this public transport. So in the Bangalore, that Ola cab is there, red buses are there. So these sensors are for city monitoring, for pollution monitoring, noise monitoring. So these devices are mobile. That means if we have the sensor for city pollution monitoring or temperature monitoring on Ola cab, this cab are moving, that means sensors are mobile. So this mesh network is for the mobile devices, not for the static. And this is the architecture of this. So here we use a 3-layer architecture. So blue color architecture indicate the Android BLE default framework of the Bluetooth, where we have not done anything. This already available in the Bluetooth. If we open the protocol stack of this Android BLE, then we can find out this there are 3 connections, scan manager and advertiser manager. All these packets are already there. And this application layer is your application. If you use the WhatsApp, that WhatsApp is your application. If you use some game, then the game is your application. This brown color is our contribution, that we have designed a mesh network where we use the 2 capsules. One is for node, other one is for connections. So first is the node. They have the node information. That means they have the routing tables, they have the state, okay, they have the objectives function, and they also have the timer that okay, how much time I am in active state and goes into the sleeping state or outside the network, and brush up or fresh up of the link that okay whether my mobile device is nearby, my mobile device is still there or they go outside. We also have two more connections. One is the child, one is the parents. So who is my parents, who is my child? So every periodically they check that after a certain period that okay my child is there, my parent is there, or they move outside. So these features is that we have added in this BLE mesh network for mobile devices. Those mesh, some of the mesh network that is already exist and that is available, that is on the repositories, but the problem is that they are not considered the mobility. So that means they are not required to consider the timers or the child-parent relation every time. So once they create the network, that means they assume that the network is sustained for a long time. But here we assume that no, network is mobile, and then definitely that devices are moving here and there. The other capsule there say the resource manager. That means how many number. That means what batteries are there, how many links are there, that type of resources. If I am overloaded, then definitely that is that in degree or out degree is more. Then definitely I just deny the new connections. Okay, I already have 5 childs. I already have the 6th child. Then I'm not able to take more loads. So that type of features we have added in resource manager. What resources are available? So there are two. Capsules we have designing and the develop in this, and this work is complete protocol and the work is in IEEE census 2015 papers is exist. This is the pictorial diagram of this one DLE mesh network. Initially a root node they start for forming the mesh network. They connected with this one, then they connected with this one, then the other node B and C working as a root node, and they also broadcast, then they directly connected with D. Another advantage or the uniqueness in this BLE mesh network is that by default the Bluetooth is for peer-to-peer communication. Okay, so the difference between Bluetooth and Zigbee is that one Zigbee one-to-many and the Bluetooth is one-to-one peer-to-peer connections. But as we see in the smartphone, when we start the Bluetooth hotspot, that is one-to-many. Why? Because they create a one sandwich layer between the Bluetooth core Bluetooth protocol stack on the Android and your application, between your application. So the sandwich layer that they provide the one-to-many connectivity, but default Bluetooth they support the one-to-one. So here we also design in this the previous framework that okay the broadcaster for multiple and the objectives function where one-to-many properties are there. So this BLE mesh network is also suitable where the Zigbee communication protocol is set. Okay. So most of these healthcare devices that we have seen, these Siemens companies and other things, they support the this Zigbee communication. So because they provide the one-to-many, they also have no such interference problem. But here we also provide the one-to-many communication properties. That's why this solution is also suitable where we need one-to-many because we already designed a mesh network. This slide they indicate that okay the prototype is working perfectly and there is no bug and nothing is there. And the beauty of the solution is also there. The forming the entire mesh network takes some milliseconds, not even seconds. Okay, so some node goes outside. We can reform the mesh network. Locally reform the mesh network which takes less than 1 second time. This is the main advantage or the beauty of this solution. Now, up to now that we talk about the sensor node deployment, we also talk about the short range communication. But short range communication communicate this information up to a certain range. Once again, new challenge comes in picture that what we can do, how we can transmit this information long range. So in agriculture field, we deploy the sensor for moisture monitoring, for plant health monitoring. Then we use the short range communication between device and device. Then how we can transmit this information to the long range. One solution is that Wi-Fi. That most of the people they use the Wi-Fi, but the problem with the Wi-Fi is the high energy consumption. Wi-Fi consumes a huge energy. And these nodes are not energy that means powered. They have the battery, a very tiny battery, or these button batteries are there. So we are not assuming that they support the Wi-Fi communication or connectivity. So the short range communication, of course, it takes the low energy. So all these icons indicate the short range communication icons, and these are the long range 5G, 4G, or LTE and other things. But of course, they cover the long range but high energy consumption. So LoRa is the intermediate. That means they have the advantage of the short range, also have the advantage of the long range. Short range, they consume the low energy. That's why they have covered the advantage of the short range, and they cover the long distance. That's why they have the long range advantage. So we have tested that okay, LoRa successfully communicate up to the 10 km if the obstacles are not there. So in Varanasi, there the Ganga river is there. So one side of the Ganga and we transmit to the other side and take the diagonal. Then we calculate the distance. So around I have done the experiment and up to the 10 km I have no problem and there is no delay there. We can successfully transmit without any hop counts, one-to-one communication up to the 10 km when we use the LoRa. Another advantage is LoRa that they consumes a very less energy. That means less than the BLE mesh network. So during this lockdown and other thing, we set up in the agriculture field in that April or May, and we directly, that means we successfully received the data in October and November without any updation or any modification in that field. That means they can successfully transmit 3-month, 4-month data without any battery recharge and other things. So that is the beauty of the LoRa protocol stack. This is a very simple architecture of the LoRa. So just we brush up the LoRa concept, that what is the LoRa. So this red color indicate the sensor which is deployed inside our smart home or smart buildings and any other thing. So LoRa, they have the two devices. One is the LoRa node, other one is the LoRa gateway. LoRa node, they collect the information and from the sensors and transmit this information to the LoRa gateway. LoRa gateway device, they collect the information from LoRa node and relay this information to the network server. LoRa gateway is not doing any processing, any other thing. That is simply a gateway between the LoRa node and the network server. Network server transmit this information to the application server for solving this problem, and the application server transmit the solution to the user or the applicant. So this is the framework that LoRa network they have used. So the LoRa network comes between the LoRa node and the LoRa gateway. Okay, LoRa node, they collect this information and transmit this information to the LoRa gateway. In between, we use the LoRa network, and after LoRa gateway, the network is same non-LoRa network or 4G, 5G, whatever you want, you can use here. That doesn't matter. But the main contribution is here LoRa protocol. So advantage, as we already seen, that the energy and the long distance. This is the two advantage in the LoRa. But of course, everything has the advantage, they have the disadvantage. So LoRa, the first disadvantage is that the limited resources. So LoRa work on the licensed free spectrum. Okay. So that in India, that is the 865 megahertz to 867 megahertz is the licensed free spectrum. Anyone can use. There is, you are not required to pay. You are not required to take the license or other things. So what people are doing, they transmit huge data in license free spectrum because they are not required to pay any cost. So whatever data is there, they can transmit, whether they are useful or not, that doesn't worry, and they are not worried about that things. So in that case, the first challenge is the limited resources. So at the same time, that means LoRa gateway, they can support up to the 6 virtual channels, SF7 to SF factor 12. Recently, I've seen that in 2020, some new literature, so some white papers comes, they use the SF factor 6 also. But this work is one of my PhD student and that time we have used, and we see that the white papers or this protocol stack, they support the SF factor 7 to 12. So they have the 6 virtual channels. That means 6 devices, they can directly connect it with the one LoRa gateway at the same time, with all these things are the same, that bandwidth or whatever is there, that bit rate and other things are the same in that case, not bandwidth, bit rate and other things are the same. So this is the SF factor 7 to SF factor 12. The 6 devices, they can connect it. If seventh device want to connect, then definitely they need to wait for some time. If they are not waiting, they also connect use the SF factor 7 as a virtual channel for transmission, then interference comes into the picture. That means 2 devices, they take the SF factor 7 at the same time, then definitely the interference comes into the picture. So the LoRa, they have the problem of the interference because the devices are more than 6 at the same time. The second challenge that we face, that the data size. That means LoRa has the maximum 27 kbps speed, okay, which is very slow. That means less than the BLE or even RFID. Okay. So LoRa, they support the speed is the less than BLE. That is the second challenge. So we are not assuming that okay, IoT multimedia purpose we can use the LoRa. We can use the IoT sensors only, where the door is open or closed, or the humidity of the water or the humidity of the moisture is less than the pump on and off. Like this, some binary information. That type of information that we can use in a low data rate in LoRa. And of course, the license free spectrum, that's where the more number of users they can connect or they can transmit their data, then interference comes into the picture. So LoRa also have a duty cycle problem. So what is the duty cycle? So in the LoRa, they implement a concept, the duty cycle, which indicates how much time you can use the LoRa. So say for example, 1% duty cycle, which indicates that out of 100 seconds, you can use the 1 second LoRa. 1 second out of 100 seconds. This indicates the 1% duty cycle. So the European country, some countries they support the 2% duty cycle, some countries they support the 1% duty cycle. And right now, the India, if we are using the network server, that definitely we need to follow the duty cycle concept. If we are not using the standard network server, then there is no cap on the duty cycle you can transmit, because no one is monitoring, no one is monitoring your data, how much time you have monitor, how much time you have transmit your data. So duty cycle is the solution for solving the LoRa problem that we can use, and we can solve the problem of the that more data transmission. So we go through the literature. Then in 2017, 18, and 19 recently work. So papers they address the interference problem, and around I have gone through the 32 IEEE journals papers are there on the interference problem. I have done the survey on March, April 2020. That time 2025 journals are there. Interference problem. So most of the papers, what they are assuming, they if they have the 100 device, they equally divide the time. That means TDMA sort of things. So the time frame is divided. So if I am transmit the data at 00, then other one transmit 001, then 002, then once again my terms comes into the picture if 3 devices are there. So that type of arrangement is there. But the drawback of this approach is that what we are observing, that if I have no such data, but I also still have slot. I have the slot, even I have no such data. If other person, they have the data, but they have no slot. And they have the duty cycle, the network is free, everything is there, but they are not able to transmit by because they have no such slot. So that type of challenges are there in 2017 paper. 2019, they use some modulation technique, TDMA and other things. But the problem is that such modulation techniques are suitable when the nodes are very less. If the nodes are huge nodes are there, then modulation techniques are also have the problem. Then definitely overcome comes into the picture. And whatever the modulation technique challenges are there, the same challenge comes into the picture here. And the 2019 have one interesting paper. What they are doing, they discard the low power signals. That means if two devices, they use the SF factor 7 virtual channels, and the LoRa gateway, they consider one node which has the high energy, other node which has the low signals power, then discard that one packets because they have the weak signal, and they assume that okay, this is not useful like this one. And data transmission purpose. So in 2019, IEEE IoT journal paper, one paper, they consider that okay, they transmit a selected data. They are not transmit the entire data. But of course, this is also not a perfect solution. And the other one paper 2018, they consider the compression. We extend this one work, and we published one paper that on the compression also in the LoRa. But what problem is that in 2018 IEEE sensor journal paper is that what they are doing, they consider the compression, existing compression technique, and the LoRa default. So they are not considered the LoRa property for compression. That means they assume that they are two independent research. One is the compression, other one is the LoRa. So they use the compression, existing compression technique, they use the existing LoRa technique and use that. But that is not a perfect solution. And what we have done, we compress based on the resources. That means the LoRa packet size is, say for example, 100 bits. We compress the data so that we can form the multiple packets, and each packet is the full packet. So we compress the data in 500 bits or 600 bits, not 520, 530 bits. Okay, so that all the packets are fully packed, not partially. So here we use the knapsack problem, 01 knapsack problem for compression of the data like this. Duty cycle problem is also there. But there, so some 2019 paper, they are not consider the duty cycle. They assume that there is no duty cycle, but that is not a practical solution. And the other one consider the large duty cycle, which is also not supporting. So these are the challenges that how authors are suggested and what solutions are there, and we find out the drawback on these approaches, and we propose the solution. So what we are doing, we use the game theory for interference problem, and Shannon theorem and 01 abstract problem for interference problem. And data compression, we use the LSTM and the other machine learning technique, but we also consider the LoRa properties. That means what is the packet size, what is the bit rate, and other things while compressing the data. And while consider the duty cycle, we consider the age of information. Age of information indicates that what is your age, what is the information age. So say for example, you generate this information at time t, and you transmit this information at the receiver side, the information received at t plus delta t. So delta t is your age. That means your information is outdated up to delta t time. Okay. So objective is there to reduce the age of information so that we make the freshness in the information. Otherwise, your information is outdated. Say for example, if door is open or closed. So you are using the network only for that means your objective is to monitor that means whether the door is open or closed. If door is open, then you can take some action like this. If gas leakage or not in the kitchen. So your objective is that that means you can find out the information within a given delta t time. That is not that if we sensor detect that okay, gas is leaked and your edge of information is 10 minutes or 5 minutes. No, that is not useful. Your edge of information less than fraction of the second or fraction of the minutes like this one. So here we consider the edge of information concept. We also consider the queuing model and POSIT graph theory concept for making the duty cycle problem and for handling the duty cycle problem. So there are 4 problems that we are consider, and so in this main idea is that I just summarize the main idea. We use the game theory in all these 4 problems. That is that means in algorithms as a algorithm we use the game theory, and in the game theory LoRa gateway is the leader and LoRa nodes is the follower. So the problem is that in the LoRa that SF factor 7 and SF factor 12 are the virtual channel, 6 virtual channel. SF factor 6, SF factor 7 is suitable a device if that is very close with the LoRa gateway. Say for example, SF factor 7 range is up to the 10 km. That means the distance from the LoRa node and the LoRa gateway is up to maximum 10 km. SF factor 12 range is around 30 km or 40 km. Roughly we can take. So that means a device they can take the SF factor 12 if the distance from the LoRa node and LoRa gateway is up to the 40 km. So that is the way that SF factor 7 10 km, SF factor 8 is 12 km, then SF factor 9 is the 15 km like this one. They can increase their coverage region or the communication region. SF factor 7 speed is very fast as compared to SF factor 12. That means SF factor 7 they can transmit a huge data as compared to SF factor 12 in a given time period. So what nodes are doing? They are very greedy. So in the mobile nodes, if I have the mobile node, I have very limited data. What I can do, I can pick the SF factor 12. Why? Because if my distance is 10 km, if my distance is 12, 14, 20, 30, 40, I'm not worried about that one. Every time I can connect it with the LoRa gateway. Why? Because I have the SF factor 12. Okay. In that case, SF factor 12 is heavy loaded and SF factor 7 is light loaded. Okay. So if everyone fight for the SF factor 12, then interference comes into the picture and the problem comes into the picture. We use the game theory problem for solving these problems. So in the game theory, LoRa gateway, they announce the price for the SF factor 7. SF factor 7, 12, 8, 9, 10, 11, 12. So what they are doing, they use the strategy, LoRa gateway use the strategy, they pick a very less price for SF factor 7 and very high price for SF factor 12. So that a very less load on the SF factor 12 nodes as compared to SF factor 7 node. So then the LoRa node, they see that okay, the SF factor 12 is very costly and I am suitable for the SF factor 7. Better I can pick the SF factor 7. Once I need the SF factor 12, I will switch for the high end, high cost LoRa speeding factors. So this is the mechanism that we have used here. So in the game theory, there are 2 players are there, LoRa nodes and the LoRa gateway. Each LoRa nodes earn revenue from the end users because this LoRa node they receive the information from the end users. LoRa nodes need SF factor for sending the data. Each LoRa node is ready to pay and LoRa gateway has the limited resources. So LoRa node fight with each other and LoRa gateway start bargaining and other things. Finally, one equilibrium comes into the picture where all the LoRa node and LoRa gateway are satisfied and all the process they can stop it here. And we find out a one stable state. Okay, so what is it? Stable state indicates that if I node I, they can use the SF factor 7 for 5 minutes, SF factor for 3 minutes, SF factor 8, SF factor 9, SF factor 10 for a given particular time period. This is the stable state that the solution is there. So this work that we consider the 3 problems we published into these 4 transition papers in sustainable computing for compression, intelligent transport system, vehicular technology, network and service. We also published LoRa work in IEEE ICC, ASICON posters. So my understanding that my feeling is that one LoRa has the space that if a PhD student they are working, they start working in this direction. My suggestion is that in place of working on the Wi-Fi or some BLE, their fight is very high and work that means the space is very less. But LoRa is the future, and SIGFOG also is the same as the LoRa. So LoRa and SIGFOG is the good one. And it's an easy way to publish. Why? Because very few work is there and problems are large number of problems are there. So we need to consider. So here we consider in each paper one new problem and address that one problem with the help of game theory along with the edge of information and queuing model and 0-1 abstract problem that is also there. So now up to this one point, we deploy the sensor, we use the short range communication from sensor to sensor and use the long range communication from sensor to the base station. Now come to the processing. If the base station, they have the information. Assume that the base station, they collect the information with the help of the LoRa, with the help of BLE, with the help of sensors. The question comes into the picture where we can solve the problem and how much percentage we can solve the problem. So first solution is that So the first solution is that if I have the information, if that one machine they collect all this information, they can try to solve their own. They are not forwarding to the servers and or the cloud. Okay, that is the one solution. The solution, they have the light processing, because this is a machine. They can support only the lightweight machines or lightweight machine learning techniques, and they also have the limited data. So their plus point and minus point is there. So that means there is no network delay, no network traffic. That is the plus point, but minus point is that means we are not able to use the heavy machine learning techniques, and we also not able to use this data size. That means a small data size is there. Now the second is the local to server solution is there. That means whatever the data is there in the local machine, we can transmit on the server and we process it. So this is suitable for lightweight, and also the data is more than that one previous one condition. Why? Because we have the server, and the communication delay comes into the picture because of the local and the communication between local and the server, and also the network traffic is also there between local machine and the server. But of course the traffic is not very high because the server is also the local. So this is the lab machine and this is the lab server like this one. The third solution is that we can directly transmit the data to the cloud. Okay. So the processing, we can solve the heavy machine processing. We have the large data size, but the communication delay is very high and the network traffic is also very high. So once machine they can detect or they can collect all the data where we can process the data, that is the problem. So what we are doing, we use this one architecture, which is known as the fog computing architecture. One edge device is there, they collect the data with the help of LoRa, with the help of BLE or whatever the processing is there, they collect the data, they transmit to the fog device. Fog device try to solve the problem, and for partially they solve the problem, and if any remaining problem is there, they can forward to the cloud for solving the problem. So say for example, we take an example of the merge sort, and we have the 10 elements. So 3 elements we can sort at this level, 4 elements we can sort at this level, and 3 elements we can forward to the cloud like this one. So some portion, some fraction of the portion we can solve at this, and at this. Maybe possible the fraction is the 0, maybe possible the fraction is the 100%. Depend on the size of the data and depend on the requirement. So this is the network architecture that okay, we can use. These are the leaf devices that generate the data. Edge machine, they try to solve the data, then forward to the fog, then forward to the cloud, and cloud solve the entire data. This is one of my PhD student work. So they have done a survey on this, and 2017, 18, 19 papers, they consider this one problem, and most of the papers they consider the energy, and very few papers they consider the lifetime. So the energy and lifetime are completely different, but people are focused on energy efficient. They are not consider lifetime prologues or enhance the lifetime of the network. So say for example, we go to the previous one figure in this. If I want to solve the energy efficient, I have the problem of the energy efficient. What we can do, we can solve the entire problem at the edge device. Okay, because edge machines, they consume a very less energy. So we are consumes a very less energy. We can try to solve the entire problem at the edge device. What's happened? Maybe possible we can solve our problem, but these edge devices goes down because they have the limited power. You can try to solve the entire problem at the edge device, there goes down, and now we have no sufficient energy for forwarding this data to the edge, to the fog, to the cloud. So the network goes dead. That means there is no communication bodies there. We are not able to forward this data. Why? Because there is no edge devices remaining battery power, and all these devices are dead, and the lifetime of the network goes down. So when we propose a system, when we design a IoT system, and then we consider the energy, we also consider the lifetime. Same thing, delay and deadline. So people are consider the delay. Their objective is to less delay, but they are not consider the deadline. Okay, a minimum delay is not guarantee a deadline. That means my task is the 5-minute task is the deadline. That means we need to solve the task within 5 minutes or whatever the time is there, and delay says there's a 7 minutes. Then the solution is nothing to be useful. Even your solution is the minimum delay. So delay and deadline both are the different. Based on the problem, we need to see that whether we focus on the delay or the deadline or both like this one. Accuracy also a problem, but very few, only 2018 paper they consider the accuracy. This red color is also an interesting part that 2017 and 18 paper they consider the complete that means offloading. That means either they solve the problem at the edge or the fog or the cloud. They are not partitioning the problem. They assume that one concrete problem is there. I am solving the problem at the edge device or the fog device or the cloud device, not bifurcate or not divide the problem into the sub-problem. And 2018 and 19 papers, they consider the partition of the problem into the sub-problem. But they also assume the fixed partition. They already prefix. That means 50% I can solve at the fog, at the cloud. like this one. They are not dynamically calculate the partitioning of the problem. So in this PhD work, we consider the deadline with lifetime, lifetime and accuracy. So there are three problems that we consider, and this is the optimization problem that we solve. The minimum of the energy consumption such as the deadline delay is less than the deadline. So very roughly I can give an idea that this, if that is the problem is the unit, and we divide the problem into x1, x2, x3 fraction, where the fraction value lie between 0 and 1. Of course, it is maybe possible it is equals to 0. It is equals to 0, x1 equals to 0 indicates that we are not solving any portion of the problem at the edge device. We solve the problem at the fog and the cloud if x1 equals to 0. If x1 equals to 1 indicate that we can solve the entire problem at the edge device. We are not solving the problem at the fog and the cloud. So this concept we are using here, and here we use the Keketi condition and Lagrangian for solving this one problem. The second problem, we along with the deadline, we consider the energy also that consumes the limited energy. And here the interesting part in the second problem, what we are consider, we also maintain the order. This is the as far as what I have done the survey, I have not find out any other work they consider the order of the task of the problem. Say for example, if we have one machine learning, then data pre-processing is the first step, machine learning is the second step. If I am dividing the problem into the two tasks, one is the data pre-processing, another is the machine learning, we are not able to swap. That means we are not able to solve the data pre-processing at the cloud, machine learning at the fog. First, you need to solve the data pre-processing, then after comes the machine learning. So this order we need to maintain. Similar as the example is the, say for example, binary search. So binary search required a sorted element. So sorting is the first step, searching is the second one. So sorting we need to do is the edge device, or is the fog, or is the cloud, and corresponding the searching is either fog or the cloud, the upper layers or the same layer, not the down layers. So if we consider these order, then only 6 cases are possible, not other cases. So we maintain the order, we maintain this one, and we use this one. We design a one prototype. So if please you go through this papers, if you find out that most of my papers, they have the prototype, they have the practical applications, not only the simulation or the mathematics. That means we try to implement the solution on the real world and find out the accuracy, usefulness of the solution. So this solution we use for the writing scale monitoring for play school, and this is for Montessori, that when Montessori or play school kids are there, that is the 3 years, 4 year old babies are there. So what they are doing, their main objective is that properly gripping the pencil. Their objective is not writing scales, monitoring and other things. So whether they are properly monitoring or whether they are properly grip the pencil or not. So here that so here we can see that okay, this the person, they use this 4 fingers for gripping. Here we can see that okay, they have this is a finger for the gripping. So most of these cases are the wrong cases. That means they are not properly gripping the pencils. So this angle is also not correct. So that type of monitoring is the second one problem. We propose a prototype for this one. So data pre-processing, of course, at the edge device or the leaf device, and machine learning at the fog or the cloud. So this is the proprietary solution, and we implement. So here we use the light blue beam plus, that is the one processing node is there, PC board is there, and on the top of the pencil we can put it here, and the smartphone, they work as the edge device, fog computing as a system, and cloud is the. So here cloud is not useful because we solve entire problem at the fog device. Cloud is only useful for transmit this information to their parents, a report card sort of thing. So if your kids they are going into the play school for 4 hours, around 30 minutes they grip the pencil. Out of 30 minutes, 12 minutes they properly gripping the pencils. And so that is the objective that in this problem that we solve this one. Third problem, that we focus using the edge and fog concept for making the accuracy along with the deadline and energy. So what we are doing, we use 2 devices. One is the edge device, other one is the fog device, and we perform the same gesture. They classify the gesture. We give the higher value for the fog device because this is a strong machine as compared to edge device, and they have the huge data, and you can use the high-end algorithms. So if the result is mismatching, then we give the higher priority to the fog device for retrain the model at the edge, and the edge device increase their accuracy periodically. After certain rounds, we are not required fog device. Edge device itself is the sufficient for finding the accuracy. So this is known as the incremental learning or machine learning techniques like this one. So here a person, they perform a gesture that okay, that volume up. So they also speak that volume up, and they also move the smartphone upward. That means the accelerometer upward. They say that okay, this one is there. But if the smartphone, they are not detect perfectly gesture, but this fog device, they detect just volume up, means increase the volume at a particular level. Then they indicate, they transmit this information to the edge device reset themselves and increase the accuracy. So the third problem, they're making the accuracy, increase the accuracy for the system. So this fog computing there, where we can solve the problem. That work is published in this Networking and Service Management Journal and Consumer Electronics Sensor Journal, and also in the conference Globecom and WFIoT conference. So here up to now we covered the IoT, Internet of Things. We consider the sensor deployment, deterministic or random anyway. Short range communication, BLE, for sensor to sensor. Long range, from sensor to the processing device. And for computing, when we can process right now, or we can wait for some time. And where we can process at the edge device, as the fog device, as the cloud device, and how much percentage we can process at the fog, at the edge, at the cloud. So this is that one direction. Now we cover up this one direction. So in this talk we cover up only the early classification as an intelligence. So early classification is this is also a very interesting direction that we find out. And one of my PhD students, Gupta, that is working on this one, and recently they submit their thesis. So the difference between the early classification and normal classification is its data size. So say for example, you need 100 accelerometer values for classification of an activity. Early classification says that the active sensor 80 or 70 sensor values are sufficient for classification. Of course, we are consider the less sensor values or less sensor samples, then accuracy, we need to compromise with the accuracy. So one question comes into the picture that, okay, the reviewer asked, when we submit this work, and the reviewer asked that, okay, if the accuracy goes down, then what is the application of this solution? Why people are using this one solution? So in some cases, say for example, we are using for health monitoring, for heart patient is there. In the morning, they are walking and suddenly they start running. Okay, their solution, that whatever the existing solution, whatever the simple classification technique, they need 100 accelerometer values for classification, whether they are walking or they are running. But this early classification, they need only 80 or 70 sample values. They are running, not walking. They are walking, not running, like this. Maybe possible they are wrong classified. That accuracy is 92%, assume that, or 90% accuracy. That means that out of 100 times, 10 times they predict the wrong. Even they are walking, they say that they are running, or they generate the alarm. So what else is there? That means only they generate the alarm. Then that walking person, they need to switch off the alarm. They need to send a message, no, I am walking, I am not running. That is the side effect. But plus point is that in the forest fire monitoring, or the building monitoring, fire monitoring, or the heart patient like this one, where very crucial conditions are there, and every second or every millisecond is also important. In that case, early classification has the advantage. If you have the false alarm, you just switch off the alarm. But if you can save the 20%, 30% time, 20%, 30% time is a crucial time in such cases. So in that applications, we use the early classification. So the complete classification required up to this one time series. Early classification, we can use up to that one. Of course, this earliness, we need to compromise with little bit with the accuracy. So accuracy is also in the threshold, but we can find out that one. So this is a simple architecture of the approach what we are doing. So we start with a fixed threshold. Threshold we find out with the Bayesian distribution and the Gaussian distribution. Okay, we out of 100 we need around 70 or 60 values. Then we start classification. If my accuracy is less than what I want, I add some more time series and classify. Once again check the accuracy. If accuracy less, add more time. And at a certain threshold, we find out that accuracy is the desired accuracy, and we are not required more time series for the classification purpose. And that is my earliness. That is the way that we have done some survey in this direction. So first thing is that a very few work is from the early classification. So right now 2019, 18 or 20, I've seen that that authors, they are working, even numbers of authors, they communicate with us in this direction, and we find out a very few work in this direction. So very easy, we can find out 3 directions for the PhD problem. So one is that one, there is no work for the different sampling rate. Some work that is exist on the early classification, what they are assuming, they assume that if I have the 3 sensors, all 3 sensors use the same sampling rate. But practically it is not true. Accelerometer, gyro, and compass. Say for example, we are consider 3 IMU sensors. All 3 IMU sensors are the different sampling rate. So, but people are assuming that the same sampling rate. In this work, we consider the different sampling rate. The other direction that people are assuming that their sensor is not a faulty. They believe that their sensor are working perfectly, but practically it is not true. maybe possibly your sensors are faulty. We check that in the agriculture field, sometime that we monitor the water level or humidity, but one plastic bag or some sort of thing comes into the picture nearby the sensor, then the sensor is not able to detect the proper water level. That is an example of the faulty sensor. Even sensor is not faulty, but the environment is the faulty, so that the sensor generates a wrong sensory data or sample data. So that problem that we are also addressing here. And the third one is the unseen class labels, where the class labels are not given. That means a new class comes into the picture. So here we also consider this one problem where we use the zero shot learning techniques. So few shot or zero shot machine learning techniques are there. They automatically find out the unseen class labels. So the contribution, that first problem that we only focus on, the here we can present only the first problem, that one is the training, other one is the testing. In the training time, we add more sample values again and again up to a threshold value. If I find out the desired accuracy, then this is my built classifier, and I find out the earliness, then we can classify. This is a very rough idea that okay, how we can solve this one problem. And we repeat this process for all the components, whatever the sensors are there, and take the majority of the component for the prediction purpose. So based on the problems, based on the applications, we published these are three problems that we find out that okay, industry informatica, transition of mobile computing, artificial intelligence. Artificial intelligence covers the survey. So that survey, that reverse, they also indicate that they have not seen any survey on the early classification. So this one is the first survey paper on early classification. And intelligent transportation system is also considered the early classification. We published an IoT paper in this, and there are the three conference papers or the posters that we have published in early classification problems. So my suggestion is that the long range communication early classification is the hot topic right now. Numbers of people they are working, but still we have the space. So being as an outcome, if we follow this one pattern, that deployment, then short range, then long range, then processing and other things. So the outcome is that right now we have 33 papers, transition papers or the journal papers. And most of these papers have the prototype. That is the uniqueness, that we are not given only the concept or the mathematics or the simulation result. We design the prototype and give the proof of concept. We also have some conference papers. And we also have 3 patents in this direction. And recently we do a contribution, an open source contribution towards the society, that IMU sensors for IEEE on IEEE data ports. So this is available on the contribution. We also find out some future direction. What else is remaining in this? First is that IoT with fog computing. So in the previous problem that we have discussed, we consider the edge, fog and cloud. We are not consider, that means we are consider bottom to top. We are not consider left and right. Okay, so we are not considered between fog and fog, we are not considered between edge and edge. So that is the space is there. If we consider both direction, that means y-axis and x-axis both, we go to the bottom to top and also left to right, then that solution is really an interesting solution. If one fog is not sufficient, other fog doing some work for that one fog. So this is the one direction that is still open, and very few work, I have not seen much work in this direction. And multimodal sensing is also one space that we are using either short range, long range communication or the sensor, not merge these two techniques together. Okay, that is the one space that we find out. And LoRa, we talk about the LoRa in terms of the interference, in terms of the energy, but we are not talking about in terms of the security or privacy. That is also a space. And recently some that means some papers comes into the picture, but not too much. I've seen that last week there's 6 or 7 papers that comes into the picture in security with the LoRa. They modify the LoRa protocol based on the requirement of the security. And last but not the least, as a long-term future research point, we can say the battery-free IoT sensing systems. So some A-star conferences, they have some paper recently on battery-free IoT sensing system. They assume that they are not required the battery, whatever the data is there, they process at the same time, without any storage or without any battery requirement. So they use the battery harvestation like solar power or other thing, a small battery. So they are not required battery, the solar power, that means the charging is going on and they also use the same time. So that is the interesting direction, and but it is a tough task. So this is a direct extension, and this is the extension where we need to do some more effort in this future direction. So thank you very much for this one, and this is my last slide.